Our next speaker is John Smart. He is the head of the Accelerating Studies Foundation, and is one of the which is one of the leading organizations at trying to bring this idea of accelerating exponential change in all kinds of domains into sort of an academic, intellectual setting, foster a lot of discussions about these changes, and he's been a great spokesman, leader of bringing these ideas to as many people as possible. So John, you have 20 minutes.
Thank you, Peter. Okay, I want to thank everybody for coming to this event today first. These issues, and it can seem kind of silly at times, but as Ray says, getting together and taking the issue seriously helps us get past the silliness and we advance the dialogue. And so that's really what this conference is about. That's what our Accelerating Change conferences are about. And thank you everybody for coming and bringing your passion and insights to this issue. So, okay, I got 90 slides. Something wrong with my brain in 20 minutes. So I'm going to give you just a cartoon of some interesting issues. If you want to go into these slides in more detail, they're available at accelerating.org/slides, along with my email if you want to discuss this further. So I'm going to give you a story in 3 acts with 3 actors. We're going to talk about the framework, which is the rules and constraints in our universe. We're going to talk about the picture, which is the reality we're creating, and we're going to talk about the painter, which is the actor, you and I, the individual intelligent actors in the system. A lot of biological analogy would be genes, environment, and mechanism. An analogy from astrophysics would be laws and constraints, the universe, and the intelligence that emerges within the universe. So Act 1 is the framework. What is the framework of accelerating change? Well, I'm going to discuss 3 things in very brief. Intelligence, something I call MEST compression, matter, energy, space, and time compression. And then a paradigm that I think is really important for understanding called evolutionary development. Only a small number of people are working in this area right now, but I think it's really, really important to the future. So intelligence first. In many ways, intelligence is the driver of accelerating change. Not driver in terms of the energy, but driver in terms of the steerage, the steering mechanism. So the word cybernetics comes from steering. And that's really what intelligence is doing. I think the best place to start, if you want to get a sense of how the universe is, as Ray would say, involved in creating information, is Seth Lloyd's book, Programming the Universe. It's kind of a quantum physicist perspective on how even at the quantum level, computations are going on everywhere. The whole space-time continuum is in the process of creating information, and we, on this planet, in this particular location, appear to be on the leading edge of not an anthropomorphic acceleration, but an infopomorphic acceleration. So we're not the center of the system, but information might be. It's also a biofelicitous system. A book, Biocosm by James Gardner, is a great way of understanding this concept called the anthropic principle, which physicists love to hate, but they can't get rid of. It's a really interesting idea about how life-friendly and intelligence-friendly our universe appears to be. And then finally, the Accelerating Universe by Livio. Every complex system goes through cycles, and one of the cycles is senescence and death. And this book and the concept of the fifth force, the lambda energy, is early evidence, I think, that even our universe itself is about 1 billion years into an accelerating disintegration. And where is intelligence going to go? Possibly somewhere we're not looking right now. Not outer space, but inner space. That's my theory, and I'm sticking to it. Okay. So to start with, to think about what these issues are, I think Wigner in 1960 talked about the unreasonable effectiveness of mathematics, kind of the rigged game. If you apply a little intelligence, these unreasonably simple equations, rules emerge that help us make intelligence a strongly non-zero-sum game. And Carver Mead made another wonderful observation. He said the microcosm is also unreasonably efficient. Whenever we play around in the physics of small scales, amazing efficiencies emerge. We don't understand why. These efficiencies are not so much due to human discovery or creativity as they are to human discovery. And that's a really interesting thing when you consider the dynamic between discovery and creativity. The guy who saw this even earlier was Teilhard de Chardin, The Phenomenon of Man. He said the universe was starting with a chemosphere and then a biosphere, and then it moved is moving now to the noosphere, this mimetic technologic substrate that's happening on our planet. He said that technology was in the process of cephalizing the Earth, giving it a head, and a really simple way to understand this phase transition is, he said, we have a planet with finite sphericity, finite size, and accelerating linkage density amongst all the actors. So what's actually happening, you put those two together, the constraint and the acceleration, and you get a phase transition. Eventually you get kind of a skin that is so dense that a new set of dynamics emerge, kind of like moving from a gas to a liquid. So what is acceleration studies? It's in the very early phases right now, defining itself. Here's 3 good books to start with to really get a sense of the history. It's unexplained. Don't look for any understanding of it in your physics or information theory textbooks in college. You won't get it right now because we haven't yet, at the academic level, given ourselves the permission to even study it seriously. Ray kind of pioneered kind of bringing out the data and helping us understand just how powerful it is, this 50 years of Moore's law, just how predictable this shrinking of transistor density, which gives us increasing speed and power, is, and how I think it's actually more a result of human discovery than it is human creativity. Software, which is on a 6-year doubling, is maybe a lot more human creativity. There's still fundamental algorithms being discovered, but in a lot of cases we're creating and we're not really sure what the optimization is. The universe isn't giving it to us. A guy named Dickerson showed that solved protein structures are a Moore's-dependent process, so there's all kinds of interesting computations, secondary computations that are just as exponential or even exponential once you have this fundament of accelerating computation in the hardware. And as Ray noted in 1999, this acceleration, surprisingly, only a few things, technology, capacity, and the information and communication sciences are probably the only thing that are surprisingly independent of socioeconomic cycles. And I think that's because in the Great Depression, a few curious people playing around with the physics of small scales, Carver-Mead's microcosm, for these amazing efficiencies to emerge. You didn't need a lot of resources, you didn't need a lot of human creativity, you just needed people looking in the right place. Now, 90 years earlier, I think the first singularity theorist that I've been able to discover was Henry Adams, one of our first historians of technology, and he said there's a rule of phase applied to history. In 1909, he published this paper, and he said sometime between 1921 and 2025, we're going to see a singularity where change, from our perspective, looks almost instantaneous. And I think that's a really interesting history. There's 2 other books here from in 1988 and 2000 that predict a singularity in 2080 or 2130, and 2 more recent books, including Ray's, that predict a much closer singularity with even narrower confidence intervals. And of course, this is all a guessing game at this stage, but the more people that get into this, the better the wisdom of crowds gets. So, mass compression is the driver, and that is something that we don't really understand. The engine, and that's the fuel, right? That's the gas. And it appears to be not evolutionary, but developmental. It's implicit in the physics of the special universe we inhabit, this very intelligent and life-friendly universe. And so we have these things, matter, energy, space, and time, which are increasingly understood, and they're producing information, which is still very poorly understood. As Tim Ferriss would say, there is no Einstein of information theory yet. We don't have one. And we're hoping for one possibly in our lifetime, but we don't have one. So what is information? We don't really understand it, but what we do know is that every new substrate that emerges in the universe in evolutionary developmental history can use massed resources to do any standard physical process or computation with surprisingly, astoundingly less resources with every new substrate. So mass compression is about continually doing more, better, with less resources. And that seems to be the fundamental driver that's pulling us, like this attractor at the bottom of this black hole, just pulling us into these faster and faster domains. So our machines are suddenly more mass efficient with each new generation. As Ray has noted, our main candidates are future computational technology, nanomolecular, quantum, even reversible logic require little or no energy. We're all moving to increasingly energy efficient, sustainable, and virtual cities. The weight of our GDP per capita goes down in all developed service economies over time. Global energy intensity, the energy consumption per person, has been flat for almost 3 decades in the developed world. We don't use more energy. We don't need to for multiple interesting reasons. So we actually, even human society itself is within probably a couple of generations of becoming resource independent with regard to energy, which is a fascinating thing. So what are the physics of a messy universe? Well, no one really knows. What we know is that this compression is driving this acceleration, and there are these emergent properties of information. It's more intelligent, it's more interdependent, it's more immune. and it's persistently incomplete over time. So it wasn't always like this. Originally, we had the hot Big Bang. Things were going very fast. And for basically the first half of the universe's developmental life cycle, things were going slower and slower until we had the emergence of the first galaxies. And then, as Sagan noted in Dragons of Eden, 77, we basically, in the second half, we have this astounding acceleration. And the closer we get to the present time, the faster and faster things go. So basically what we have here is a U-shaped curve of change. It looks like a developmental cycle. No one really understands why it exists. No one understands even if it's an artifact or not. I don't think it is. Cycles suggest recurrence. Probably the best person physically who's attacked this problem is Eric Chason in his book Cosmic Evolution. He says that there's a free energy rate density curve that looks like a Moore's law curve writ large in the universe. And he notes that suns, like our star, have actually 4 orders of magnitude less free energy rate density in them than our human bodies do. That's because there's a lot of energy, but they're huge, fluffy, non-dense systems. And our Pentium chips have almost 7 orders of magnitude more free energy rate density in them than the human brains do. And that's the way it seems to work. We don't understand why, but that's how it works. So I've got some laws of technology. These are tongue-in-cheek. They're just rules of thumb. But I would say first thing to realize is this, from Chason's model here, is that technology learns 10 million times faster than you do, and it always will. And if you recognize that, then it's incumbent upon us to make technology an extension of our humanity. Because it's going to learn and continue to learn and pick up these cognitive modular singularities 10 million times faster than we do. You know, this watch here does calculation. It's a calculational singularity for me. I have no idea what's going on the other side of it. But I have crafted the structure of this watch so that it really serves my ends. And more of those calculational singularities are picked up modularly as we move to this thing we call general AI. Another thing to realize is that humans are selective catalysts and not controllers of our technological evolutionary development, and the first generation of any technology is often dehumanizing. And so it's incumbent upon us as designers to try and get beyond that hurdle. There's 5 classic strategies that are discussed for technological development, the so-called NIBIX pentad. Only 2 of those, I think, are in this acceleration phase: nanotechnology and information technology. As Archimedes would say, they're the levers that are moving the world, and we need to realize how special they are. As one example, some researchers were playing around with a structure called a photonic crystal in 2004, and they figured out that they could make microlasers 1,000,000 times more energy efficiently than we'd made them in 2003. Not 100 times, not 1,000 times, but 1,000,000 times. That's the jaw-dropping efficiency advance that happens in the nanospace. We don't understand why it is. We still don't put the kind of resources, funding, attention to the nanospace or the infotech space the way we do other spaces. But when we do, these amazing advances occur. A more pedantic example, Toshiba had the lithium-ion nanobattery last year. They announced a nanobattery that recharges lithium-ion 80% in 60 seconds. That's almost 80 times faster than the lithium-ions you have in our cell phones today. Playing around with the physics at small scales, nanostructured lattices at the cathode and the anode. That's all they did, and look what popped out. Now, you might think, okay, that's not so disruptive, but put it together with plug-in hybrid vehicles, and you have a car that could fill its nano battery gas tank faster than it can fill its gasoline gas tank. And you have an energy independence transition for the next 20, 30 years if you want it. Okay? And a lot of people are looking at this right now. So the thing to understand with mass compression is technology is now the fastest layer. In terms of hierarchical systems of social change, it used to be all about the money, or all about the power, then it was all about the money, and now it's all about the technology. And so these layers have reorganized to fastest first, and we need to understand just how powerful the technological hierarchical system as a tool for social change has become. And the power of technological benevolence, as Buckminster Fuller would say, using an incredibly compelling technology, like a cell phone, and pushing it out to everybody for free. Probably the first person to really see this was Buckminster Fuller, and the full scale. He had a term for mass compression that he called ephemeralization. He said that we're moving away from needing resources. All progressions are from more material to more abstract. They eventually hit what he called the electrical stage, sending virtual bits to do physical work. This trend has also been called virtualization, or weightlessness, or as I call it, mass compression efficiency or density. The last thing that we should say, this is very speculative, is if every new substrate uses vastly less matter, energy, space, and time to do its encoding, Doesn't it look like the future? Everything else in outer space is slow space compared to what's in inner space. It's computationally slow. It's very simple. It's rapidly encapsulated by our simulation space. I put it to you that this thing right here, this brain, is basically a massive simulator that's actually modeling the birth and death of the universe on, what is it, a few watts, right? Now, I look at structures like the space station, which is a non-autonomous system, and I don't think that's anywhere near as interesting as this system right here. And I think it's only when our technologies become as organic and as completely simulating, as natural, fault-tolerant, redundant, biologically inspired as these systems, will we finally see a technology that becomes what we would consider a natural extension of ourselves. The handle on this that I think everyone needs to get is something called evolutionary development. I think it's a new paradigm for change. Evolution is random, chaotic, it's unpredictable, it's expansionary. Development is exactly the opposite. It involves the calculation of optima, okay? Local optima, but still optima. So this happened in the Cambrian explosion. We had differential multicellularity, and then within the next 10 million years, we had 35 body plans that were computed. There have been no new body plans for the last 500 million years. Okay? The development of brains undergoes a process everyone calls neural Darwinism. It's exactly a left-hand, right-hand process. And so is, as William Calvin would say, the way that unconscious thoughts compete with the thoughts that you want to throw out on the conscious level. So EvoDevo is extremely helpful as a tool, and I think if you want to see the difference between them, look at two genetically identical twins. At the microstructure level, everything is molecular chaotic selectionism. It's unpredictable. And at the macro level, look at all those amazing similarities between those systems. Both evolution and development are working in that system, and one drives unique local and one drives predictable global patterns. Marbles, landscapes, and channels is another way of looking at this. The marbles roll around in the landscape, which is the system. They take unpredictable paths, but together they converge on these low-energy channels, and that's the mass compression attractor at the bottom of the basin. This model is being used right now to attack biogenesis in a new way that I haven't seen since I've been studying the field. Eric Smith at Santa Fe says, look at potential prebiotic chemical reactions. They form a vast possibility space in the energy landscape. A subset of these make self-reproducing, self-varying chemical cycles. Those produce information, which permanently modifies the selection environment, so-called niche construction. That now modified selection environment has a series of low-energy paths constraining the landscape. Okay. Now, can we understand how biogenesis is going to be an inevitable developmental emergence from molecular chaotic determinism? I think we might. And that doesn't take away the incredible generativity of evolution itself as a system. It's just the other half of the picture that's currently not being done. Evolution doesn't understand how many eyes you need. It throws as many as it can at the wall, like this three-eyed skink, but development pairs it back to the optimum. Same with four-wheeled automobiles. Probably the best example, the most aggressive example I've seen of this is Russell's dinosauroid hypothesis. If you remember the raptors in Jurassic Park, they had opposable thumbs, they had forward-facing eyes, they were pack hunters. They were tending massively towards what he calls the anthropoid form, and that's where they would have gone if there hadn't been a KT meteorite in this model. Will we be able to simulate this in future simulation science? I think so. So evolution and development are two fundamental ways of looking at the system. The deepest question is when, where, and how they interrelate, and that's what we need to get to. And I think for political dialogues, innovation and sustainability are two really important left and right hands of change. If you only have one, you're missing half the picture, because EvoDevo needs both. So development also follows trajectories. We have Maslow's hierarchy, and there's also a technological learning. Angus Madison showed phases of capitalist development. Now we're moving towards a networked society, actually more than that. And now we're actually moving out of network to what several people call a metaverse or an attention economy. And this is an ICT-enabled services sector, and it's a fascinating thing to watch. So the framework challenge here is building EvoDevo theory in a world dominated by debates between evolutionists and creationists. Evolutionists, in most EvoDevo models, only see half the picture, and creationists probably see less than the other half, right? So we're in a really, really tough spot right now where we really don't have a good dialogue. So the picture is acceleration mechanics, immune systems, intelligence amplification and AI. You need to understand things like the S-curve and how they saturate, things like the D-curve, which moves towards decline and recycling. All living systems do this. I'd like you to think about the difference in the S and the D curve, right? Logistic growth and recycling, between germline, which are the cells in us that are immortal, and somatic cells, which are the cells in us that are continually recycling. They follow two different sets of dynamics. Developmental systems highly protect the immortality of the parameters, but they have evolutionary expendability in the expansion of those parameters into the computational net. If you understand that difference, then I think you understand deeply why the only kind of immortality we might see in the coming decades, and here I differ with some of our speakers, is what we might call a cybernetic immortality. At the biostructural level, we're built to fall apart at an accelerating rate after sexual maturity. It's encoded in our fundamental structure, and it's actually valuable to us for that falling apart to occur in a competitive evolutionary environment. And we're in the process of transitioning to a system that is, in many ways, biologically independent. Nanotechnology may get us there, but I think information technology is getting us there even faster. So the last curve I'm going to leave you with is the J curve. And here's where we have second-order hyperbolic growth. It's made of first-order components, singularities all the way along. And at each level, some aspects of the post-emergent, post-limit systems can't be understood or guided by pre-singularity systems. And that's kind of the state that we're in today. We see this wall, we see the threshold coming up. We have tremendous opportunities for the future. And I think the important thing is to develop the awareness, have the courage to advance the dialogue. Thank you for your time.
We're going to